I'll start question 1 by multiplying both sides by x plus 2 squared, x plus 5 squared. I will then cross out the denominators with the corresponding bracket from the numerator, and I will take everything to the left-hand side. I will take x plus 2 and x plus 5 as common factors, and now I will expand these two brackets here, and then I will collect like terms. Now I will factorize this quadratic, and now my function is a product of 4 linear brackets. Each one will give me a critical value, and I'll put all the critical values on a number line. Now, if I expand this bracket, this will be a positive x to the power of 4 function, which means when x is very large, y will be large as well, positive, and these signs will alternate between the critical values. And from the inequality sign, less than 0 means negative below the x-axis. So these are the two regions I want. So my solutions are x between minus 5 and minus 4, or x between minus 2 and 1. For part A of question 2, I'll start by writing the given fraction as follows: a over r plus 6 plus b over r plus 8. Then I will merge the right hand side into a single fraction, and I will remove the common denominator. So I get 1 is equal to a r plus 8 plus b r plus 6. Next, I will let r be equal to minus 6. This will make the second term disappear, so I'm left with 1 is equal to 2a, so a is equal to a half. I will then let r be minus 8, so I'll get 1 is equal to minus 2b because the first bracket will disappear, so b comes out to be minus 1 over 2. So now I can write the original fraction into two separate ones, and I can even take the 2 in the denominator and have my final form as 1 over 2r plus 6 minus 1 over 2r plus 8. For part B, I need to find the following summation. Notice, with the exception of the 2 here, everything else is equal to my expression in part A. So I can write this summation as 2 times the 2 partial fractions I found, and now that 2 can cancel out with those 2's and get this form. So now I will let r be equal to 1. So I get 1 over 7 minus 1 over 9. When r is 2, I get 1 over 8 minus 1 over 10. When r is 3, 1 over 9 minus 1 over 11. And I can keep going up until the term r equals n minus 1, which will give me 1 over n plus 5 minus 1 over n plus 7. And finally, when r is equal to n, the last term, I get 1 over n plus 6 minus 1 over n plus 8. Now note that this minus 1 over 9 with the 1 over 9 2 rows below will cancel out, and this pattern will continue. So everything on the first column except the first 2 terms will cancel out, and everything on the last column except the last 2 terms will also cancel out. So if I put everything together, I'll get the following: 1 over 7 plus 1 over 8 minus 1 over n plus 7 minus 1 over n plus 8. I will calculate the sum of 1 over 7 plus 1 over 8. This will give me 15 over 56 minus the other 2 fractions. And now I will combine everything into a single fraction. So I get 15 times n plus 7 n plus 8 minus 56 n plus 8 minus 56 n plus 7 over 56 n plus 7 n plus 8. Next, I will expand these brackets here. I have one more expansion to make. Then I will collect all the terms in the numerator. And finally, to get the required form, I will just factor out the n in the numerator, and this is my final answer. For part A of question 3, I'll start with this transformation and rearrange to make y the subject. So I get y is equal to z to the power of minus 1 over 2. Next, I will differentiate this. This will give me dy dz is equal to minus 1 over 2 times z to the minus 3 over 2. Next, I want to get dy dx in terms of z and x only. So I will use the chain rule, dy dz times dz dx, and dy dz will be this expression I have found above. So now I can go to equation 1, which is this one, and replace dy dx and those two y's with what I have found above. So I get this equation. I need to multiply those two powers to remove the brackets to get this result. And finally, I need to get rid of this. To do so, I will multiply by minus 2z to the power of 3 over 2. And I will get this result, which is equation number 2. In part B, to solve this equation, I first need the integrating factor, and to find the integrating factor, I need the integral of the coefficient of z. So the integral of minus 4x dx is minus x squared. So the integrating factor is e to this result. So the solution of the differential equation z e to the minus 2x squared is given by the integral of the right-hand side of the equation times the integrating factor. And if I simplify by adding those two powers, I will get this integral. And if I proceed and integrate this, I will get 1 over 3 e to the minus 3x squared plus c. So to get z on its own, I will divide both sides by e to the minus 2x squared and get the following result. So now in part C, I want a solution for the differential equation 1. So I need to replace the z with y to the minus 2. Here it is. Now to get y squared as required, I will write y to the minus 2 as 1 over y squared. And then for the right-hand side, I'll just write this as a single fraction. So I can now flip those two fractions and get y squared on its own. Now I don't like that 3c that appears there, so I will replace that with another constant. Let's call this constant a. Now this is a valid answer, but if you want, you can multiply top and bottom by e to the x squared to get this alternative form. For question 4, I'll start with this transformation and try and make z the subject. So let's cross multiply. Zw plus w is equal to z minus 1. So if I collect all these z terms on the right hand side, I'll get w plus 1 is equal to z minus wz. Then I'll factorize the z on the right hand side. So w plus 1 is equal to z1 minus w. And then to get z on its own, I will just divide by that bracket. So z equals w plus 1 over 1 minus w. Now let z be the complex number x plus iy and w be the complex number u plus iv. So if I replace this z and these w's by these complex numbers, I will get the following: x plus iy is equal to u plus iv plus 1 over 1 minus u plus iv. Next, I will separate the real and imaginary, so I get the following. U plus 1 plus iv for the numerator and 1 minus u minus iv for the denominator. So now I can realize the denominator by multiplying by the complex conjugate. So I'm multiplying by 1 minus u plus iv, both top and bottom. So if I expand, this will give me the following. Now each term is obtained as follows. For the real part of the numerator, I've got u plus 1, 1 minus u, plus iv times iv, so minus v squared, because I squared is minus 1. And for the imaginary part, this is the sum of those two products. Now for the denominator, I get 1 minus u squared plus v squared, which is essentially minus I squared v squared. These two products will cancel out. And if I simplify now the real and the imaginary part, I will get the following: 1 minus u squared minus v squared for the real part, plus 2vi over 1 minus u squared plus v squared. Now I will equate the real and imaginary parts of each side. So I get x, which is the real part from the left hand side, is equal to 1 minus u squared minus v squared over 1 minus u squared plus v squared. And for the imaginary part, I've got y is equal to 2v over the same denominator. I'm given that y is equal to 2x, so I'm going to use that. Y is equal to 2x, and if I substitute the x and y from above, I will get this equation. Now I can cross out the denominators, and I also can cross out the 2, and this will simplify to the following: v is equal to 1 minus u squared minus v squared. I'm going to take all the letters to the left hand side, so u squared plus v is equal to 1. I will complete the square for the v, so u squared plus v plus a half squared minus 1 over 4 is equal to 1. Take the 1 over 4 to the right hand side, so u squared is equal to v plus a half squared is equal to 5 over 4, which is the equation of a circle. The center is 0 minus a half, and the radius is the square root of the right hand side, which simplifies to root 5 over 2. In part C, I need to solve the following inequality: y less than 2x. This implies that the left hand side of the circle equation is less than 5 over 4. Now the circle has a center of 0 minus a half, so if I draw the circle, I'll get this one, and because I have less than the radius, I want the region inside my circle, so this is what the required region is. For question 5 part A, I need to differentiate cot x. Now there is a standard result for this. This is minus cosec squared x. In order to find the second derivative, I need to differentiate again, and I need to use the chain rule. And the derivative is minus 2 cosec x to the power of 1 times the derivative of cosec x, which is minus cosec x cot x. And if I multiply those cosec terms, I will get 2 cosec squared x times cot x. Now the question only requires cot x terms, so I will use the identity that says cosec squared x is equal to 1 plus cot squared x, and get the following result. And if I expand this, I will get 2 cot x plus 2 cot to the power of 3x, which is the required answer. For the third derivative, I will just repeat differentiation. Cot x again gives me minus cosec squared x with the 2 at the front, and then for these I'll have to use again the chain rule, so I get 6 cot squared x times the derivative of cot x, which is minus cosec squared x. Let's again replace the cosec squared x with 1 plus cot squared x. Note I have moved that minus at the front of the term. So now if I expand my brackets, I will get minus 2 cot squared x minus 6 cot squared x minus 6 cot to the 4x. And if I simplify, I will get this result, which is in the required form. For the Taylor series expansion in part C, I need to start by evaluating y and the derivatives when x is equal to pi over 3. So y at x equals pi over 3, or more simply f of pi over 3 is root 3 over 3. If I replace pi over 3 into the first derivative, I get minus 4 over 3. Repeat for the second derivative, you get 8 root 3 over 9. And finally, for the third derivative, you get minus 16 over 3. Then just use the Taylor series expansion as given in the formula sheet. So you'll get cot x is equal to root 3 over 3 plus minus 4 over 3 x minus pi over 3 plus the second derivative, x minus pi over 3 squared over 2 factorial, and finally minus 16 over 3 times the bracket to the power of 3 over 3 factorial. And then if you simplify, you get this, which is the final answer to this Taylor series expansion. For part A of question 6, I'll start with the auxiliary equation, which is m squared minus 2m minus 3. I will factorize this and get m minus 3 times m plus 1 is equal to 0. And the solutions are m is equal to 3 and m is equal to minus 1, which means that the complementary function is y equals ae to the 3x plus be to the minus x. The right-hand side of the differential equation is a trigonometric function. So for the particular integral, I will try y is equal to p sine x plus q cos x. If I differentiate, I will get dy dx is equal to p cos x minus q sine x. And if I differentiate again, second derivative equals minus p sine x minus q cos x. So let's go back to the differential equation. Here it is. And replace the second derivative, the first derivative, and y with what I have above. This will give me minus p sine x minus q cos x minus 2 p cos x minus q sine x minus 3 p sine x plus q cos x is equal to 2 sine x. Now I will equate the sine and the cos terms of the left and right hand side. So for sine x, I have the following: minus p plus 2q minus 3p is equal to 2. If I simplify this, I will get minus 4p plus 2q is equal to 2. If I divide by 2, I get minus 2p plus q is equal to 1. This is my first equation. And then for cos x, I get this. So minus q minus 2p minus 3q is equal to 0. And then if you simplify, you get minus 2p minus 4q is equal to 0. Let's solve these equations simultaneously. So if I subtract the two equations, I will get 5q is equal to 1. So q is equal to 1 over 5, which will give me p as minus 2 over 5. So the particular integral is y equals minus 2 over 5 sine x plus 1 over 5 cos x. Therefore, the general solution, which is equal to the complementary function plus the particular integral, is y equals a to the 3x plus b to the minus x minus 2 over 5 sine x plus 1 over 5 cos x. So now let's use the boundary conditions that I'm given. When x is 0, y is 0. And if I substitute this into the general solution, I will get 0 is equal to a plus b plus 1 over 5. So a plus b is equal to minus 1 over 5. I have another boundary condition, but I will need the derivative. So differentiate the general solution, dy dx is equal to 3ae to the 3x minus be to the minus x minus 2 over 5 cos x minus 1 over 5 sine x. And now replace x equals 0 with dy dx is equal to 1. And this will give me 1 equals 3a minus b minus 2 over 5. Therefore, 3a minus b is equal to 7 over 5. Another two equations to solve simultaneously. So if I add the two equations this time, I will get 4a is equal to 6 over 5. So a is 3 over 10, which means b is minus 1 over 2. And if I replace everything into the general solution, I will get the particular solution, y is equal to 3 over 10 e to the 3x minus 1 over 2 e to the minus x minus 2 over 5 sine x plus 1 over 5 cos x. For part A of question 7, I need to verify that the point of intersection of the two curves is this point. So I'll do that by replacing theta by pi over 3 in both equations and getting an R value of 3 over 2 and making a valid conclusion. So let's do that. When you replace theta by pi over 3 in the first one, you get 3 over 2. Same value when you do that in the second one. And a final conclusion like, therefore, curves intersect at P will conclude part A. For part B, I need to find the shaded region. Let's start by labeling the two curves as C1, C2. C1 is the circle, C2 is the cardioid, and if I join the point of intersection to O, I split up R into two regions. Now R1 is bounded by the blue line and C1, while R2 is bounded by C2 and the blue line. So I'll use two separate integrations to find two regions and then add them together. So the formula for the area when you have polar coordinates is the integral of 1 over 2 r squared d theta. Now replacing r with root 3 sine theta will give you 3 sine squared theta inside the integral. Now I'll take 3 outside as a common factor, and then I'll be left with sine squared theta. And in order to integrate that, I will use the following identity: cos 2 theta equals 1 minus 2 sine squared theta. So if you rearrange this one and substitute, you'll get 3 over 2 integral of 1 over 2 minus 1 over 2 cos 2 theta d theta. Now for the limits, I'm using the lowest value of theta up to the theta that corresponds to the point of intersection. And now I'll take 1 over 2 out as a common factor, so I will get 3 over 4 integral of 1 minus cos 2 theta. So when I integrate, I get theta minus sine 2 theta over 2. Let's substitute the limits. This will give me pi over 3 minus root 3 over 4 for the first substitution and 0 for the second. And when you simplify, you get the area for R1. Let's do the same for R2. If you substitute R as 1 plus cos theta, you get this one. Let's expand. This will give me 1 plus 2 cos theta plus cos squared theta. Now I know how to integrate those two terms, but for cos squared theta, I need to use a double angle again. The double angle I'll be using is cos 2 theta is equal to 2 cos squared theta minus 1. And if you rearrange this one, you will get 1 over 2 plus 1 over 2 cos 2 theta. So let's add those two terms together. This will give me 3 over 2 plus 2 cos theta plus 1 over 2 cos 2 theta. So now I am ready to integrate. Doing so, will give me 3 over 2 theta plus 2 sine theta plus 1 over 4 sine 2 theta. And the limits I'll be using is for the lower one, the point of intersection, and for the upper one, that's the maximum value of theta I have in the question. So let's replace and get this value for pi and this value for pi over 3. When you simplify, you get the following: pi over 2 minus 9 over 16 root 3. So finally, let's add together R1 and R2 to get R. So pi over 4 minus 3 root 3 over 16 plus pi over 2 minus 9 over 16 root 3. If you simplify, you get this value. Take out a common factor of 3 over 4 to get the final answer. For part A, I need to show that the expansion of this gives me this expression. So let me just rewrite the original expression. I'll take out the power of 3 as a common power. So I get this one. I find this easier because the expression inside the square bracket is just the difference of 2 squares. So then I can just apply the binomial expansion with a power of 3. That will give me this expansion. Note that the coefficients when the power is 3 are just 1, 3, 3, and 1. If I simplify this, I get the following. So now I just have to rearrange. The question requires the power of 6 and the 1 over z to the 6 together, and then everything together with a minus k as common factor. So if I do that, I will get the following. So k is 3. Now in part B, I will start with z equals cos theta plus I sine theta, and I will use De Moivre's theorem so that z to the power of n is cos n theta plus I sine n theta, and also z to the minus n is equal to cos minus n theta plus I sine minus n theta. Now I can use properties of cos and sine, where cos of minus n theta is cos of n theta, and sine of minus n theta is minus sine of n theta. Therefore, z to the n plus z to the minus n is cos n theta plus cos n theta, which will give me 2 cos n theta. Similarly, z to the n minus z to the minus n will be obtained by subtracting the two expressions above. So I get I sine theta minus I sine theta, which simplifies to 2I sine theta. So letting n be equal to 1 in those two will allow me to proceed to part C. So I have z plus 1 over z cubed, z minus 1 over z cubed. I can replace each bracket with each of these expressions, and if I expand the right hand side, I'll get the following: 8 cos cubed theta times 8I cubed sine cubed theta. Now the left hand side, I'm just using the result from part A. Now I'm gonna use part B and replace those two with the expressions I found in part B with n6 and n2. So I'll get 2I sine 6 theta for this expression minus 3 times 2I sine 2 theta for this expression. Now 8 times 8 is 64. I cubed is minus I, hence the right hand side. Now on the left hand side, I'll take out 2I as a common factor. So now I can divide both sides by minus 64I to get the following, which is what I'm supposed to show in part C. In part B, I need to find the following integral, and I will use the result of part C. So this is equivalent to finding this integral. I can integrate both terms, so I will get minus 3 over 64 cos 2 theta plus 1 over 192 cos 6 theta. Let's replace the two limits. So replacing theta by pi over 8 will give me the first bracket. Replacing theta by 0 will give me the second bracket. And when I expand the brackets, I get the following. And I can make this into a single fraction and get 8 minus 5 root 2 over 192.